Um, okay, hello. I'm Lee, and I and my teammate member Shimbo, Daniel, Brandon, Laura, Monica, we complete our project. And the title of our project is Utilizing Edge Cloud Computing to Enhance the Data Integrity for Medical Data. Next slide, please. Next. Oh, yeah. And this is our content. We will present introduction, related work, proposal solution, simulation design, result, and conclusion. Next slide. Okay, first let me give some background. As medical technology continue to develop, the size and the complexity of medical data are also increasing. How to effectively process and analyze such massive medical data has become a major challenge facing the field of medical informatization. Traditional data processing methods such as centralized data storage and processing can no longer meet the growing demand for data processing. At the same time, the privacy and security of medical data are also facing serious challenges. And the emergence of blockchain technology provides new possibilities for solving those problems. Blockchain provides a decentralized, secure, and transparent way to store and share data, helping to solving issues such as data integrity and privacy protection in medical data management. However, blockchain technology still faces performance bottlenecks when processing large-scale medical data, especially when achieving efficient data processing and analysis while ensuring data integrity. Um, ensuring the integrity and privacy of medical data, optimizing the performance of the blockchain, and improving the speed and efficiency of data processing have become urgent issue to be solved. Next slide, please. In fact, low latency processing and analysis of medical data is not just a technical challenge. It's a matter of life and death. Delays in medical data processing may lead to incorrect medical decisions, delay patient diagnosis and treatment, and even endanger the patient's life. Similarly, if data integrity is compromised, incorrect medical decisions can also be made that could impact the patients. So in this work, our motivation is to find a balance between data integrity and latency or efficiency that is to reduce the latency of data processing as much as possible while ensuring the integrity of medical data. So our objective is to optimize the existing blockchain-based edge cloud medical data processing system. Specifically, we want to encrypt and process medical data by using homomorphic encryption technology, which can not only ensure data integrity, but also avoid high computing overhead of traditional blockchain systems and reduce computing latency. And next, Monica will introduce some related research and cases.
Yeah, thank you, Indy. Yeah, in this session, I'm going to discuss about enhancing data security and computational efficiency through optimizing decryption process in edge cloud architecture using homomorphic encryption. So our focus is on improving data security and reducing computational overhead. So coming to the importance of data security here, ensuring data security is a paramount in today's digital landscape, especially with the increasing risk of security breaches and data loss. And here, the Homomorph HE offers a solution by allowing computations on encrypted data without decryption, thereby enhancing computational efficiency. So here, the three fundamental steps in HE are key generation, encryption, and decryption. In key generation step, the process begins with generating encryption keys essential for securing our data. And in encryption phase, we can encrypt our data using these keys, transforming it into an unreadable format to ensure confidentiality. And in data processing, performing computations directly on the encrypted data using homomorphic encryption. So in decryption step, the processed data, we can decrypt the processed data to obtain the original data. So by storing the encryption keys, we can secure the keys for future use. And lastly, if we need, we can decrypt the data back to its original form using the decryption keys. Now, talking about the types of homomorphic encryption. Next slide, please. Yeah, here HE algorithms usually categorized as partial, somewhat, and fully homomorphic, as illustrated in the figure. Here in partial HE, this type allows us to perform either addition or multiplication operations on the encrypted data. Examples include RSA, which focuses on multiplicative operations, and the Pylar crypto system, which adopts an additive approach. And in somewhat HE, it allows for multiple operations on encrypted data, but within certain limitations. So the BGN algorithm is a notable example of SWHE. And coming to fully homomorphic encryption, FHE, it is the most advanced type, allowing arbitrary computations or unlimited additions and multiplications on encrypted data. So the CKKS scheme exemplifies this capability, especially useful for arithmetic or real numbers. Coming to the challenges in public cloud system. In public cloud systems are vulnerable to security breaches like risking unauthorized access and potential data loss. So compromising data integrity and confidentiality is a challenge. So when data is outsourced in plain text, it is like sending confidential information without any protective cover, so making it easily accessible to unauthorized entities. So it's a challenge. So to address these challenges, homomorphic encryption emerges as a pivotal solution. It allows us to perform computations directly on encrypted data, ensuring data security while processing. Next slide. Now, proposed solution is going to discuss by Shaiva.
Hello, I'll discuss about our proposed solution. So our proposed solution actually divided into two different tasks. One is the data access and another is how the data is retrieved from the edge and cloud. So this is the overall workflow for our data storage and data access and the network architecture. Here, the blue marks actually represent the steps during the data insertion to the edge and cloud, and the black arrow indicates the process during the data access. So our whole proposed solution has a basically divided into you can say the four different major things. One is cloud server and the homomorphic encryption and the blockchain. There is a two different levels of users. One's data owners and another is the data users. So there is a two levels of edge server we are designing. One is for the data owners part and another is for the like data users part. So I'll discuss all the content one by one in the following slides. So let's talk about the data owners. So basically, in the traditional previous works, the hospital and doctors are the data owners, but which led to a high chance of data leak issues from the hospital side. So the patient doesn't have any control over those data. To solve this issue, actually, we make that patient actually the own their data, and the patient will verify upon request from the data users and send the encryption key and the authorization to the hospital management. The encryption key will be needed to access the data on the edge in the cloud. And so, for example, any new data comes to the picture, the blockchain will initialize and send to the private key along with the encryption key to the edge server. The edge server will be distributed to the edge devices of data owners. So this encryption key will also store in the edge servers, which will later used by the data users when the data gets approval from the data owners. So let's talk about the data users. In our design, there is two levels of data user. One is the hospital management and another is the doctor. So basically here the management will handle all the relevant authorization before approving doctor. The management will send the approval key to the doctor, and with this key the doctor can actually request from the cloud server to get the reports of the patient, and management also sometimes needs more data which they will access from the edge server, like the patient info of name, age, those things from the edge server. We'll discuss about this edge server in the details when we discuss in the next about the cloud server and the edge server. So talking about the cloud server and edge server design, so every patient currently in the medical has a two types of data. One is textual data, which is like name, age, and those appointments, and another is all the reports. The report contains like imaging and all the sensitive information. So the edge server will actually utilize the L2 cache mechanism to store the basic information, because the data user needs to access those data to the frequently, and due to time constraint we cannot show the cache design. So using the cache help us to mitigate the latency, and which we will show in our result tentatively we can assume. But so on the other hand, we also store all the reports in the cloud. Both data are actually verified by the blockchain. The blockchain store the encryption key used during the report access by data user. There is also generated verification, just like unique keys in both of the cloud server and the edge server, so that there is no data mismatch for the particular patient. So for the blockchain, basically the blockchain component of the system initiated with the hashing of a press and report, and which is then recorded on the blockchain to ensure data integrity and immutability. Key management is integral of that part, with the blockchain handle the initialization and generation for keys for new data. This likely includes both encryption keys and for securing the data, and the verification of the verification keys for later authentication things. So next I'll talk about the how we design our homomorphic encryption from inherited from the previous slides presented by Monica. Actually, the whole proposed solution, this is the encryption overflow from the proposed solutions. So basically, these three keys is generated from the blockchain, and out of these three keys, like public keys, private keys, and encryption key, to encrypt data, we use a private key and the encryption key. So we use the fully homomorphic encryption, and which is the addition version. There's a two versions for the fully homomorphic and encryption. One is the addition, and another is the multiplications. So we use the addition one. So this is the basic function for the homomorphic encryption addition. So here the P is the plain text, and C is the ciphertext, and K is the encryption key. So this and ciphertext later on we can use that for the traditional and homomorphic encryption mathematics to encrypt the data of ours. So and actually that so then the encryption key is later shared with the data owner. So it is shared with the public key through another data owner level edge servers. And that hash function we are tentative to use as a SHA hash functions. So next, our fellow member will be discuss about the edge cloud SIM.
Thank you. Okay, so we use Edge Cloud Sim to simulate our proposed scenario, but before we get into the simulation, I'm going to go over what Edge Cloud Sim is. So it is an open source Java-based simulator, and the software program can be used without needing the physical hardware aspect to run the simulation itself. The program is tailored for edge computing applications built upon Cloud Sim. So Edge Cloud Sim extends its capabilities significantly to effectively model edge cloud computing scenarios. So Edge Cloud Sim is composed of 5 different modules, one being networking, which manages the data transmission over networks and behavior within the edge computing environment, including the latency, bandwidth, and packet routing. Load generator provides the realistic workloads that simulate what is being requested from edge computing. Tasks are generated in accordance to a Poisson distribution, meaning it will give the probability of a discrete outcome. Core simulation provides the necessary infrastructure that is needed to model the edge cloud scenarios. Mobility module is tasked with representing the movement patterns of devices within the edge environment, aiding in the assessment of device impact. So in this setup, each mobile device is assigned an X and Y coordinate, which are dynamically updated using a managed hash table. And Edge Orchestrator, which functions as a centralized controller responsible for distributing computational and networking resources among both edge devices and cloud servers. And the picture to the right is just the module of the load generator. So next slide, please. So how does Edge Cloud Sim works? It provides various files that are utterly available for developers, researchers, or anyone that's wanting to use the environment. And these files are config.properties file, which manages the simulation settings. So the user can go in and manipulate the settings how they like for their own preference. Application.xml stores the application properties. The edge devices.xml defines the various edge devices. The Cloud Sim will read the parameters that are provided within these files to streamline the simulation process. So ultimately, the user still has the capability of going back and editing all these files, but they are provided by Edge Cloud Sim to use without any modification if needed. Users have the ability to sample the environment by using sample applications with already existing script, compile.sh, or a new script can also be written. The script uses Java files and is both compatible with Mac OS and Linux machines. So further running the simulation, it uses run scenarios.sh which will execute the simulation, gathering all the information that is provided in the files, and the iterations can be compressed into an output file, which ultimately can be used with MATLAB to construct graphs, which we'll be seeing in a few slides. And what MATLAB is just a programming platform that can be used to analyze the data and design or create the modules. And then lastly comes the analyzing of the results that are outputted. So Edge Cloud Sim helps with providing users with metric results, which can be used with the analysis of the data from the simulation results, and then the ability to compare the different scenarios that are being used. And the performance metrics that are being analyzed by Edge Cloud Sim are the throughput, the resource utilization, energy consumption, and the response time. And then we're going to move over next to go into the simulation. So next slide. Okay, thank you.
So to obtain the parameters for the simulation, we need to obtain the computational requirements for the encryption methods in mind. So our first decision would be to pick the homomorphic encryption algorithm that we wanted to use and the one that would have minimum latency. And so we ended up picking Tensile, which is based off of something Microsoft made because Microsoft has their own homomorphic encryption method called Seal, which is pretty popular. A fork of that library for bigger data encryption is called Tensile, which has two different schemes. You might have seen it mentioned before in the presentation, but CKKS is the scheme that we chose as it's better suited for high-speed encryption and decryption for bigger data than its counterpart. So after we decide the most suitable homomorphic encryption method, we need to compare it to a more traditional mean. So AES is very well known, and that'd be the good candidate to compare our proposed standard to. So using a cryptography library and the Tensile library in Python, we're able to benchmark the two encryption methods, giving them an arbitrary amount of bytes. And then the results showed that AES could encrypt and decrypt in less than a second, and Tensile CKKS took almost 4 seconds to do so. But in the end, we use these computing times that we gathered to determine the parameters for the simulation. Next slide.
So we took the Tensile and AES benchmark data from the previous slide and altered the Edge Cloud Sim environment to show these findings. For Tensile, we made it so that when the load generator generates a task, it had a length of 2100 kilobytes with edge utilization at 21%. And for AES 128, we set the task length to 1050 and the edge VM utilization at 7%. This made sense to us because the encrypting with Tensile required the servers to perform more computations than AES 128. And when we tested it, we found our CPU usage to be much higher with Tensile. Next slide. So moving on to the results of the simulation. On this slide, we're starting out our AES results. You can see the graphs produced by Edge Cloud Sim showing the processing times and servicing times for tasks in the simulation, as well as the number of devices when those times were recorded. In the graph legend, you can see that it says 1 tier, 2 tier, and 2 tier with Edge Orchestrator. And what it means is that in tier 1, the tasks produced by the Edge devices are completed by the closest Edge server. Tier 2 means that all of the requests are processed by the central cloud for the Edge servers. And Tier 2 means that the Edge orchestrator for the simulation will assume that all Edge servers are on the same network and offload an overloaded Edge server onto another Edge server. For this simulation, our intention was to simulate just the Tier 1 only, but because of our lack of time, we couldn't figure out how to remove the other two environments from the graphs, and that's why you see them on the results. Since we're just looking at tier 1 for the results, we're just looking at the red lines on the graph. On the left figure, it shows the processing time on this as the simulation increased devices. And on the right, you see the service time with the same increase in devices. We see that as the number of mobile devices increased, the processing time and service time had an upward trend before seeming to plateau around the 4-second mark. The service time peaked at 3.9 seconds at 900 mobile devices, and the average processing time peaked at 3.82 seconds. Next slide. When looking at the VM utilization for AES simulation, we can see that it's similar to the previous figure, except this one changes pretty heavily once it crosses 800 devices. You can see it steadily climbs up to 62.83 utilization and drops down to 48.28 at 1,000 devices. Next slide. Moving on, we have our 10-seal CKKS simulation results. We have the processing time on the left and the service time on the right. The results show that the times in both graphs grew at a much greater pace than the AES results, and they never really plateaued. At 1,000 mobile devices, the service time reached 6.39 seconds, and the processing time peaked at 6.31 seconds, which was almost double the times of the AES simulation. The reason I mentioned that the 10-seal result don't plateau is that it signifies that AES encryption environment might be better for scaling up with more devices. Next slide. When we look at the average VM utilization for 10-seal, we can see that the utilization was at 70.29% with the device count at 500, and it steadily decreased to 53.96 at 1,000 devices. We suspect that this is because the tasks in our configuration file were made to be larger for the 10-seal simulation, and the servers were unable to take on as many tasks as the AES simulation, so the utilization dropped off while the service and processing time increased. So now I'll be handing it off to Brandon with some closing thoughts on the simulation.
So to just kind of sum up what those graphs show is that AES is just more practical and efficient. It's more lightweight and it's widely used. So it scales better when an environment has a large amount of devices, but conversely, 10-seal offers better security and scales well when there's less devices in the environment. So, and you'll also suffer from high computational overhead using that method. But in the end, homomorphic encryption would be implemented in a medical environment if it was smaller and data privacy was of utmost importance, and you could suffer the cost of high computational overhead. But we believe that overall the simulation could be a bit more fine-tuned and tested had we provisioned more time. There are also other homomorphic encryption libraries that aren't widely known, which could also yield even better results if we had time to simulate them. Next slide.
Okay, this is our conclusion. First, the project demonstrate the potential of integrating blockchain technology with edge cloud computing to enhance data integrity of medical data. And based on this, homomorphic encryption is introduced, allowing encrypted data to be processed without decryption, maintaining data integrity while still enabling its practicality. And then through our simulation and experiments, we found that different types of encryption method have different advantages and disadvantages. So specific choice of encryption method should be changed based on actual needs. That's presentation of our project. Thank you.